Good evening, everyone. Welcome back to week 12 live session. So today we will compile all the examples that we were discussing regarding the MOSFET spectroscopy. And there are some additional examples, how we can have mixed valence compounds and the metals, the iron specifically, how we can distinguish them. And we will be having certain assignment problems. Now, tomorrow would be the last live session that I'll be taking. That's an extra session for you guys because in the earlier stages when we were discussing the group theory and the point group symmetry related questions, a lot of topics came, but we have not given more attention towards the character table formation. So I will be taking up the extra session for covering up that topic, which might not be involved in too much in syllabus, but questions probably will be coming from that. So to give you better understanding of the character table, we will be discussing it tomorrow with certain examples. Also, I will try to cover up whatever we have discussed in all these 12 weeks of time, including today's lecture, regarding the cellular dichroism as well as MOSFET spectroscopy, the group theory part. All the three aspects would be covered tomorrow. So try not to miss that. Timing would be 5 to 7 p.m. Tomorrow is Sunday, so I hope you will be there for last lecture. That would be beneficial for you to attempt many questions from the character table of the group theory part, which you were facing difficulties earlier. So right now it's 7:04, and we will wait for 2-3 minutes for others to join, and then we can start with uh, with our session. Thank you. Before we begin with our last session for including all the weeks, is there any doubt regarding the sessions that we have covered so far? And if not, then we can begin with our session. So these questions we will take up. Some questions are added from the previous session. So because that are covering most of the topics from mass spectroscopy. And today, firstly, we will start with the last section of examples. So lastly, we have ended up regarding the mixed valence complexes. So in this particular situation, how the MOSFET spectroscopy helps us to identify iron, different kinds of iron are there, or it's a similar kind of iron, their oxidation state, their spin value. So that we will get to know from the spectra. And we will be covering the examples regarding this mixed valence complexes. So just to give you a brief introduction regarding that, what we had discussed last time. So we have classified mixed valence complexes in basically three types. Class 1, which is called the localized ions. If they are localized, obviously they would be indistinguishable. So if I have a complex with where iron 2 is existing as well as iron 3 is existing, and localized means both of them, they are at their position, there is no electron transfer is happening in between them, and we can easily identify through the mass bar spectroscopy. There would be two different peaks, for one peak for iron 2, one peak for iron 3, and as suppose they both have same spin state, and we know that iron 3 would be having more negative delta value compared to the iron 2, so we can expect to have the, say, I'm not showing the splitting over here. I'm just considering a case where it is only the iron 3. And if I am talking about iron 2, it would be in this particular position. So this value is of iron 3 plus, and this is of iron 2 plus. So this unit is velocity, millimeter per second, and on the y-axis we have transmittance. So I hope this is clear. So when we are saying that this comes under a complex, we have two different iron, or there could be many different irons. Like number we are not defining. We are just saying that iron are existing in two different oxidation states. One is +2 and one is +3. If they are localized onto themselves, they are not delocalizing. Delocalizing means if there is no transfer, if there is an electron transfer occurs, it means iron 2 goes to iron 3 and iron 3 becomes iron 2. So whether we can distinguish them or not. So here when we have one separately group for the iron 2 and one for the iron 3, so we can separate them. So they come under the category of distinguishable. And localized ions. Now the second example that we have is class 2 is where we have delocalized ions. That means if I have iron 2, iron 3, they would be in equilibrium with iron 3, iron 2. That means if I'll mark this as A, it as B, then A will convert to this A, iron 3, and B will go to iron 2. So now this A has gone to this particular, so their transfer has occurred and they have now become delocalized. So what if I have still, I can still see these two peaks. So this one for iron 2 and this one for iron 3. So this is a case where it is delocalized. That means electron transfer has happened, but still this is distinguishable from the spectrum because we can see both the peaks for both iron 2 and iron 3. Okay, so the third class that we have is class 3, which says, so this is delocalized ion which are indistinguishable. In this particular case, what we are having iron in 2, iron in 3 that occurs as an average of iron 2.5. So this particular peak appears. So when both of them, they are having an average oxidation state of plus 2.5, then we will be seeing only one signal. Here I've already mentioned that I'm not considering the splitting of the one particular peak. So I'm just taking one peak over here where I'm considering the EFG value is 0. So if EFG is existing, electric field gradient is existing, then we'll be having a splitting of these two values. So right now we are not considering that. So ultimately we ended up having class 1 as localized and distinguishable. Class 2 we have delocalized, that means transfer is happening, but they are still distinguishable because we can see the peaks of both iron plus 2 and iron plus 3. In the last classes, it is delocalized. That means the electrons transfer has happened. But due to the average oxidation state, they become indistinguishable because both of them, they are now existing as 2.5 oxidation state. Now, how their mass bar spectra will look like. So here the y-axis is your transmittance, x-axis is your velocity. And if I'm starting with this particular state, so this is the case where I'm considering that EFG is non-zero for all the cases. That means splitting will occur. So this is the spectra observed at 287 Kelvin. Okay. Now I will draw. So this is still there. With now low intensity. And mainly what occurs, one peak here, or we can just make it a bit broader. Now the second case would be again these two peaks, that splitted peak, and here we have I hope you are understanding the point that whatever the middle point is there, we are maintaining it. And here, now I'm saying at 287 Kelvin, we were having one peak which got split into two. Now, when I'm reducing the temperature, I can see two different peaks to be appearing, but still they are overlapping and their averages is matching with the first case. Now, third one that we'll be having. So we can see these green and red ones only. Now the now at 250 Kelvin, black trace is removed already. That means whatever the thing that we were having here, that has been removed now, and only green red traces are appearing. And at last, what we are observing, so red appears here, going this direction, and green also is coming separately here and here. So they are now not crossing, they are distinguishable properly. So this occurs at 115 Kelvin. We are taking certain case where we have both the irons in coordination or in a complex, which is called a mixed valence. For example, I'm taking this where it is iron and This is in Rn2, and this is further bound with another ring, which is connected with Rn3, and so on, so forth. So here we have one Rn centered in Rn2, another Rn centered in Rn3. So as the spectra says, now you need to read very carefully. So we are saying that at higher temperature, we are seeing the case where one peak has split into two. As I have taken the case where EFG is existing, so one peak is splitting into two, and this peak is this one, this black trace. Now, what is this black trace? Both of them, that one peak is only there, and we are saying we have two Rn, one is 2 plus and one is 3 plus. And if we are seeing only one kind of signal, that means both of them, they have averaged into Rn 2.5. So this case is class third. This was in Rn 2.5. Now, if we are decreasing the temperature, their delocalization is stopping, and then it is again coming up. Like Rn2 is also appearing and Rn3 also is appearing. So as we know that Rn3 is having more negative delta value, so we can expect this red trace to be Rn3 and this green trace to be Rn2. And Rn 2.5, it is the average of both. It is the average of both Rn in +2 and Rn in +3. So up to this point, is this clear, or should I repeat it again?
Okay, ma'am, clear.
So as you can see, when we are decreasing the temperature, that means we are restricting the molecule to not to have any kind of electron transfer, and that has to be localized. For example, if you are giving some sample heating, so the electron movement got randomized and their movement gets started. When it is freezed, their movement would be freezed, and that is called as localized. So when we were having a high temperature 287, both of them got delocalized and we got an average oxidation state of 2.5. That's why one signal we can observe which got split into two because of the electric field gradient. As we are reducing the temperature, we can see that two peaks are coming. That means both Rn2 plus and Rn3 plus, they are appearing. That could be a condition of they are delocalized, but still they are distinguishable. And at last, when temperature is lower from 287 to 115, both the peaks of Rn3 plus and Rn2 plus, they are distinguishable and they are now localized. As they are not overlapping with each other, so they are separated. So they come under the class of 1, where it is localized and distinguishable. This one is the case class third, where it is delocalized as well as indistinguishable because only one kind of peak is coming. And in between what we are having, that is a class 2. So is this clear how mixed valence complexes with two different oxidation states of iron, we can identify in what state, in what temperature they are going to exist. So is this clear? So we will take up the next example. This was just a brief introduction regarding the mixed valence complexes. So our main example that we are going to take is, so we have ended up having the 8 examples last time. So 9th example that I am continuing with, we have, so taking a system where we are considering ligand and we are taking an acetate ligand. So we know that how acetate appears. So acetate is nothing but CH3, C double bond O, O negative, which seems to be in this particular form. This is your methyl group. This is your one oxygen. This is your other oxygen. Since it can go under resonance easily, so they will form O negative here, and this is double bond. And ultimately, you can have, or we can just write how it forms when we have CH3COH, that is acetic acid. It's a weak acid, so that's why we are showing the equilibrium sign. It makes the acetate. So this is your acetate and it has lost a proton. Now this acetate is our ligand, which we are showing here. When we have CH3, when we have CH3, it is bound with carbonyl group. Double bond O is here. It is like this way. Now it comes here. This double bond goes onto the oxygen. It will form CH3, C double bond O. So now this will form negative and this will form double bond O. Now you can see the negative charges between both the oxygens. So ultimately it will give you a resonance structure where oxygen, other oxygen, this kind of negative charge shows that it is localized on both the oxygens. So now if you will see carefully, when we have ligand is having or binding with metal or with the one side, out of all the atoms, if it is bound with one atom, that is called monodentate ligand. And if in this particular case, if I'll say that both the oxygens are playing role and it is actually a bidentate ligand because both can participate in forming a coordination bond with your metal system. So that is called a bidentate ligand. Also, they can be bridging ligand also because one particular system can bound with other metal. With one metal, it is fine. That can also be bound with the other metal. So that's why in this particular example, we have 3 iron coordinated with the acetate system. How they are coordinated? Firstly, we will form. So if you will see, this is OCOCH3, that's your acetate. The negative charge is on both of them. Similarly, and this is the methyl group. Similarly, one more acetate group is there, which is having negative charge. Here also, we are having oxygen, oxygen, there is carbon, this is CH3. So another oxygen. So as you can see here, firstly, from the ligand, both the atoms are participating. That is called a bidentate. Secondly, from the ligand, when both the atoms are participating, they are coordinating with two different metals. They are called bridging because one oxygen is bound with one iron metal, other is bound with another one. That is called the bridging one. Similarly, for the third oxygen, a third set of iron. So this is negative and this is also negative. And how they are connected with each other? So they are connected by using a oxide linkage. So oxygen, 2 negative, oxygen having 2 negative with the lone plus, that is making coordinated bond with the 3 metal centers. So this is in between. And to complete its coordination, right now it's making 5 bonds. So there is one more ligand attached. So we have a nitrogen. And similarly here. So now its coordination number of 6 is completed and all the 3. Now we need to find how these 3 irons are connected with each other. It has been found that 2 irons are in +3 oxidation state and 1 iron in +2 oxidation state. So how do we confirm that? Firstly, we'll check the charge. If 1 iron is in +3, 2 irons in +3, that will give you +6, and 1 in +2, that is giving you +2 over here. That means total charge, positive charge is +8. It should be balanced with the total negative charge because there is no negative anion is outside. So if we'll consider how many acetates are there, 1, 2, 3, 4, 5, and 6. So we have 6 acetate and each acetate gives you -1 charge. So this becomes -6. And there is one coordinating oxide that is O2 negative, so -2. So this charge is balanced with +8 and -8. Net charge is 0 because this is a neutral ligand which is not giving any charge to the system. So is this clear? How are we balancing? So this comes from the theoretical thing. Okay, we are expecting it to be 2 irons in +3, 1 iron in +2. So up to this point, is this clear?
Ma'am, once again, that is 6 acetate equal to -6 means
Mix. We are talking about right now here charges. So 1 acetate gives you -1 charge. 6 into -1, it's -6. So I'm just writing.
okay, ma'am.
Okay.
O2 minus, ma'am. O2 minus.
Oxide, that is giving you a -2 charge. So we are just taking up the ligands and the metals and we are counting what is the total positive charge, what is the total negative charge. It has to come 0 because this whole complex is neutral. It is not having any charge.
Okay, ma'am. Okay, I understood.
So now here we are expecting theoretically it should be 2 Rn should be in +3 and 1 Rn should be in +2. So let's see through the, so this we have expected and it has been found that this complex when we are using two different solvents when we are using, first is benzene, second is methyl chloroform. So that behavior is different over there. So we will see from the how mass per spectroscopy can help us to identify the different behavior in benzene. And we have expected iron in +3 is to iron in +2. It should be a ratio of 2:1. That means whatever the signals we are going to get for iron 3, it should be having twice the intensity compared to the iron 2+. So first case we are taking for when it is stabilized in benzene solvent. So how your transmittance is going to look like. We have transmittance here, and this is your velocity, mm/second. So I will explain the reason firstly over here. As you can see, here we have a pyridine kind of moiety, which is having an ethyl group over attached at the para position. So this is a pyridine. Pyridine is also an aromatic system. You can see this double bonds are there, right? So when we have another aromatic system, which is benzene. So this solvent is again an aromatic system. So because of their intermolecular forces, the benzene rings get tagged onto this particular complex, which restricts the transfer or the delocalization of the all the irons. So if iron, this, I'm just making like this tri system. So if I'm expecting this A, this B, and this C. So both A and B, I'm expecting it to be +3. And this is an I'm expecting in +2. As I said, that it is 2:1. So when I'm using a benzene as a solvent over there, it actually stabilizes the system and it does not let that transfer to happen and delocalization could not be possible. So here, delocalization becomes restricted. So when delocalization becomes restricted, that means they are localized onto their positions and no transfer is occurring. So when they are localized, whenever they are localized, they would be distinguishable. So we can see easily the peaks for iron 3+, iron 2+ with the required intensity. So here I'm going to draw how the graph that we are obtaining. So firstly, we got this one. And the other one that we got is, so you can see approximately this ratio is 2:1, right? So the red peak, firstly, the red one, that iron one has to have more negative delta value, right? So this one becomes your iron 3+ and this is your iron 2+. And also, as I said, their peaks have to be 2:1 ratio, so that we are getting at 298 Kelvin. So this is fine. Now, when we are going from 298 to 120 Kelvin also, that means we are reducing. Even at higher temperature also, delocalization is not happening and we can easily see the peaks over there. And these peaks remain as such when we are going to lower temperature. So it has to be 2 times what we are getting for green trace. So we don't see any kind of changes happening from going from a higher temperature to lower temperature in case of benzene. Because we were expecting in earlier case, as I was explaining here, when we are having a high temperature, the transfer happens and delocalization happens. And that's where we can see that, okay, it can go to average state of plus 2.5 oxidation state, or there could be any transfer. But here in this particular case, at high temperature also, it is showing 2 particular peaks with the proper splitting. That means both Rn2 and 3 are still localized. They are not moving anywhere. And anyway, when we will decrease the temperature, nothing is going to change the particular spectra. So both the Rn3 and Rn2, they are localized here and they are easily distinguishable in case when we are having a benzene solvent. Why is it happening? Because benzene is itself stacking onto the molecule, which is making it to be highly stabilized. And because of the intermolecular forces, there is less movement, or we can say it is no more a dynamic thing. And whatever is staying at the first, their particular position, they will stay at. That Rn3 will stay at this position, Rn2 will be staying at this position. There won't be any transfer happening. So is this example clear? And then we can move to another solvent. Any doubts on this one?
No doubt.
Okay. Now we will look at the spectra that we have obtained when the solvent has been changed. So in the solvent CH3, CCl3, how it looks like. So we'll first draw the spectrum. This is transmittance. This is the velocity. So firstly here what we observe, we are getting at 298. And when we are going down, we're almost expecting it to come. This is as 240. Then it what has been observed that here 2 peaks kind of they were merging, and as the temperature was decreasing, the peak started coming and its intensity was increasing as we were reducing the temperature. So in earlier case, we saw similar kind of spectra. Even if we are going for high temperature to low temperature, there both the peaks were defined. But in this particular case, if you'll see at the high temperature, we can have at the high temperature, we see only one kind of spectra, one kind of peak is there. That means this particular case is delocalized and it is indistinguishable. Only one peak is there. 3 different irons out of 3, we said 2 are same and 1 is different. But here we are getting the spectra only for 1. That means all 3, they are having an average of Rn 2.5. So this is a case of class 3rd mixed valence complexes at the high temperature. As soon as we are decreasing the temperature, delocalization moves to the localization and they attain their Rn 3 plus and Rn 2 plus. So low temperature, they become localized. So that's why the solvent also plays a very important role when we are observing a MOSFET spectroscopy. We need to see whether the solvent itself is having any kind of interaction which is stabilizing a molecule. The dynamic nature of that ions to convert to other one, that has been stopped. So we will be observing this kind of spectra where distinguishably we can have the iron 2 plus and iron 3 plus. But when we are having a solvent which is not participating in it, and therefore the dynamic nature increases, so iron 3 plus can transfer the electron to other iron because there is a bridging ligand over there. And through the transfer, that average environment of iron 2 plus is 2.5 is coming, and that is why the first one is indistinguishable, only one peak is coming. As we are decreasing the temperature, we are restricting their movement, their dynamic nature, and therefore we can easily identify iron 3 plus and iron 2 plus. So is this concept here, how the solvent also plays a very important role in identifying the different metal systems, different irons in a mixed valence complex. So is this clear?
Clear, ma'am.
Okay. So now we can take up another example. Example number 10. So here, this example, again, the mixed valency complex we have to take. So we have iron, cobalt, and iron. Earlier we were having iron, iron, and iron. Here we are having another metal system. Even though we know that cobalt is not MOSFET active, but how the cobalt interactions is going to change the MOSFET spectroscopy through the bridging ligands. So here what we are having 3 nitrogens. These 3 nitrogens are bound with a ethyl group with each other. And similarly here, both the irons are in same atmosphere. This I'm drawing with. This is also having bonding time, another, and this one. So all the 3 nitrogens are interconnected with the ethyl group, and how they are connected with the cobalt. So they are connected with sulfides, 3 sulfides, completing their 6 coordination number. And these sulfides also are connected with the nitrogens. I'm showing with the dotted lines. This is a ligand only, what we are having. So we are expecting iron 3 low spin, cobalt 3 low spin, cobalt 2 low spin. And here also iron 3 low spin. So when we are expecting both the irons are in same spin state as well as oxidation state, so they should give you a similar kind of spectra. So here what we are going to have. Now we will quickly look at its MOSFET spectra. So firstly, at 353 Kelvin, what we observed, we got this kind of peak. After that, we started seeing that this blue trace is decreasing with lowering of the temperature, and ultimately it vanishes. what is happening here at reducing the temperature, we are seeing a new peak coming here. And here it is even more intensity. And at last it is almost equal intensity here. And also we observed that in addition to this one, we are having a small peak here, which is coming like and ultimately it is equal intensity. So what we observed over here is that we were expecting that iron all the two irons are in iron 3 plus state, but since at 353 they are having an average environment and it is giving you 2.5. As you can see, its delta value is in between the two values. So if this is more negative, this could be of iron 3 plus, this could be of iron 2 plus, and the middle one is iron 2.5. As soon as we are decreasing the temperature going to 5 Kelvin, we observe only iron 3 low spin, and this is iron 2 low spin. Why we are saying iron 2 low spin in this one? Firstly, the delta value has to be less than the iron 3, but why the splitting is so less? So how the mass per spectroscopy could tell us that when we are decreasing the temperature from 353 to 5 Kelvin, how the two irons which were expected to be in +3 oxidation state, they are going from 2.5 to coming to iron 3 and iron 2. So this happens if we consider iron in 3 plus. So when we are